Ever feel like you're stuck in a loop solving the same problem over and over, but like the pieces are always changing?
Yeah, I know that feeling.
It's the whole deal with these repetitive combinatorial optimization problems, or RCOPs as the cool kids call them.
Right.
They're everywhere. Scheduling tasks, routing vehicles, even like optimizing how data flows through networks.
Absolutely. It's a challenge that comes up in so many different fields.
We're taking a look at this research paper today. It's called Graph-Based Deterministic Policy Gradient for Repetitive Combinatorial Optimization Problems. Quite a mouthful.
Yeah, that's a bit of a tongue twister.
But this deep dive, it's going to give you a fresh perspective on how to tackle these tricky RCOPs.
I think what's really fascinating about RCOPs is they build on those classic optimization problems, you know?
Like finding the shortest route or the best possible schedule.
Exactly. But then they layer on this constant change.
Okay, so walk me through this.
The underlying structure of the network, the basic connections, those might stay the same.
Right, I'm with you.
But the details are constantly shifting.
Traffic conditions, demands on the network, available resources, that sort of thing.
Exactly. All of those things are in constant flux.
So it's not a static puzzle then. It's more like, I don't know, juggling while riding a unicycle.
That's a pretty good analogy. You've always got to be adapting on the fly.
And to make things even harder, it's like there are all these rules you have to follow.
Right. The hard constraints, those add a whole other level of difficulty.
Think safety regulations in a plant or bandwidth limitations in a network, those kinds of things.
Exactly. Those constraints really limit your options for finding the best solution.
It's like the universe is throwing every wrench it can find at you.
Pretty much.
But people have been working on these problems for a while now, right? What are some of the approaches they've come up with?
Well, traditionally, there have been two main camps, centralized and distributed solvers.
Okay, so break that down for me.
Centralized solvers, they aim for that absolute best, most optimal solution.
Makes sense, but
they can be slow, and they need a lot of computing power, especially when you're dealing with large networks.
yeah, I can imagine a supercomputer crunching numbers for hours just to figure out the perfect delivery route.
Yeah, something like that.
Not exactly ideal when you need answers quickly.
Right. And that's where distributed solvers come into play.
Okay, so what's different about these?
They break the problem down into smaller parts. This way, different parts of the problem can be solved in parallel.
So it's like having a team of computers, each tackling a piece of the puzzle.
Exactly. It's much faster. But sometimes you might end up with solutions that aren't quite as perfect.
A trade-off then. Speed versus absolute perfection.
You got it.
But wouldn't it be amazing if we could have both?
The best of both worlds, a system that's fast and accurate.
Exactly.
And that's where this research gets really interesting. They're proposing this new approach they call GDPG twin.
GDPG twin. Okay, I'm listening. Tell me more.
It uses machine learning. And I think it has the potential to really crack this challenge wide open.
Okay, I'm intrigued. What's the secret to this GDPG twin thing?
Well, they're combining a few really clever techniques. The first is graph neural networks, or GNNs for short.
GNNs.
Think of them like AI detectives, specifically designed to understand these complex relationships within networks.
So they're not just looking at individual data points, they're looking at the whole web of connections and how those connections are always changing.
Precisely. And to help these GNNs learn, they're using something called deterministic policy gradient.
Okay, now we're getting into the technical stuff.
It's a type of reinforcement learning. It's like giving the AI feedback on its actions.
So rewarding it for good decisions and discouraging the bad ones.
Right. That way, it can constantly improve its decision-making.
So it's not just analyzing the network, it's actually learning how to manipulate it to get to a certain goal.
Exactly. But then it gets even cooler.
Oh, there's more.
They're also using something called twin networks. It's like having two GNNs working together.
Okay, so two AI detectives working the case. I like it.
One of them guides the solution process. The other predicts what's going to happen. And they're constantly learning from each other.
Becoming more efficient and accurate over time. That's pretty neat.
It really is.
But does it work? Did the researchers actually put it to the test?
Oh, they absolutely did.
Yeah.
The results, they're pretty groundbreaking. They tried GDPG twin on a bunch of classic RCOPs, and it showed some remarkable improvements over existing methods.
Okay, like what? Give me an example.
Take the maximum weight independent set problem, or MWIS.
MWIS.
Catchy. It's like this. Imagine you have the network of points, each with a certain value or weight.
Okay, I'm picturing it.
And the goal is to find the set of points that aren't directly connected.
Yeah.
And you want the set with the highest total weight.
Like picking the most valuable, non-overlapping spots on a map.
Exactly. Now, existing algorithms, they can solve this. They don't always find the absolute best solution,
Yeah.
especially when you're talking about big, complex networks.
Right. And this is where GDPG Twin comes in.
GDPG Twin was able to close that gap by a third. Think about it like finding a delivery route that's 33% closer to the absolute shortest path.
Wow, that's a pretty significant improvement.
It is.
Did they try it on any other types of RCPs?
They also tackled the minimum weight dominating set problem, or MWDS.
MWDS, all right. Another acronym.
This time, it's about finding the smallest set of points that could reach all the other points in the network.
So like strategically placing cell towers to make sure you have coverage for a whole city.
Exactly.
Okay, now I'm starting to see how this could be applied in the real world.
Right.
So how did it perform on this MWDS problem?
Depending on the type of network, it improved solution quality by as much as 11%. And there's more.
I'm all ears.
They even tested it on a real-world problem, optimizing data flow in a wireless network to minimize delays.
Huh. How did it do?
It was just as accurate as a much more complex method, but 5 times faster.
Okay, now this is exceeding my expectations. Efficient, adaptable, effective, and it works in real-world scenarios. This GDPG Twin is starting to sound like a real game changer. But before we get too carried away, the paper, it mentions this thing called random sampling around the current policy when they're training the twin networks.
Right.
Can you break that down for me a little?
Sure.
What does that even mean, and why is it important?
Well, it's all about making sure the AI doesn't get too narrow-minded. You see, one of the really cool things about GDPG Twin is it can learn and adapt even when the network structure itself isn't changing.
Okay.
But if we keep feeding it the same information over and over again, it might get stuck.
Stuck in a rut.
Yeah, exactly. It's kind of like, if you only study for a test by looking at one practice problem.
You might ace that problem, but you won't really get the concepts.
That's the idea.
So to avoid that, they introduce a little randomness into the training.
Exactly. So instead of using the exact same policy parameters all the time, they sample slightly different values.
Okay, so it's like slightly adjusting the settings on a machine to see how it performs under different conditions.
Yeah, that's a good way to think about it.
That way, the twin network gets a more robust understanding of the problem. It doesn't get stuck in one way of thinking.
Right. It's a really interesting application of what we call exploration exploitation in reinforcement learning.
Exploration exploitation. Got it.
Yeah.
The paper also talks about comparing GDPG Twin to, what's it called? Zeroth order optimization, ZOO.
Oh, yeah, ZOO. It's another technique for figuring out how to improve your solution, especially when you can't directly calculate the gradient.
Okay, back up for a second.
Sure.
What's the gradient in this context?
It basically tells you which direction to move in to make your solution better.
Got it.
ZOO. What it does is it tries to estimate this gradient by randomly sampling points and seeing which direction leads to better results. So both techniques, they use random sampling, but in different ways.
So what's the key difference, though?
Well, the main difference is how they use the information from those random samples. ZOO uses multiple samples to estimate the gradient directly. It's a bit like trying to find the highest peak in a mountain range by randomly picking spots and seeing which way is uphill.
Okay, so it's a bit of a brute force approach.
You could say that, and it can be really computationally expensive because you have to evaluate the system a bunch of times for each step.
So how is GDPG Twin different?
A GDPG Twin, it uses the twin network to learn from the sample data. It builds a model of the problem. It's like, ZOO is hiking blindfolded while GDPG Twin is using a map.
That's a good way to put it. So it's more efficient because it's not just taking random steps, it's learning and adapting.
Exactly. And the research actually shows that GDPG Twin doesn't need as many evaluations to get the same level of performance as ZOO.
Which makes it a lot more practical for real-world situations where speed matters. This is really interesting stuff. I'm starting to understand why this research is such a big deal. We've been talking about independent RCOPs, where each problem is treated separately. But I noticed the paper also mentions RCOPs that are embedded within a, graph-based Markov decision process.
Ah, yes. Now that's where things get really interesting.
This is like next-level stuff. So what does that even mean, and how does GDPG Twin handle it?
Well, up until now, we've been talking about solving one problem and then moving on to the next.
Right, like each problem exists in a vacuum.
Exactly. But in the real world, that's not always the case.
Of course not. Our decisions today often have consequences for the future.
Exactly. The decisions we make now, they influence the next problem we need to solve.
It's like chess, right? Every move sets up the board for the next one.
Perfect analogy. And that's where Markov decision processes come in, or MDPs.
MDPs, got it.
They give us a framework for making decisions when our actions have long-term consequences. So with RCOPs, it means that solving one problem will directly affect the next one. It's like a chain reaction.
So it's not just about solving one puzzle, it's about playing the whole game strategically.
You got it.
Okay, but how does GDPG Twin even approach that? How can it learn to optimize for the long term?
The key is that it can anticipate those future consequences. Remember, in the independent RCOPs, we're only worried about the immediate problem.
Right.
But with RCOPs and an MDP, the AI has to develop a strategy. It has to think several steps ahead.
So it's like the AI is going from being a tactical problem solver to a strategic mastermind.
Exactly. It's not just trying to solve one puzzle at a time. It's learning to play the whole game.
That's amazing, but how do they even test something like that?
They used a really good example from wireless networks. Delay-oriented distributed link scheduling. Imagine a bunch of devices that are constantly sending and receiving data.
Okay, I'm with you.
The goal is to minimize the delays in those transmissions. But the amount of data each device needs to send, it's always changing. And the network itself might be changing too.
So it's a classic RCOP, but now with the added complexity of those long-term consequences.
Exactly. They actually compared GDPG Twin to another method that's specifically designed for this type of scheduling. GDPG Twin performed just as well, but it was 5 times faster.
So it can handle those complex scenarios. This is all pretty incredible.
But before we get lost in all the excitement, I gotta ask.
Yeah, what's on your mind?
We've seen what this GDPG Twin can do. It's impressive.
Right.
But every new tech, it's got to have some limitations,
Oh,
right?
for sure. And to be fair, the researchers, they do point out a few in the paper.
Okay, like what?
One thing they mention is they want to look more into the variance and worst case scenarios.
When it comes to the optimality gap, you mean?
Yeah, exactly. GDPG Twin, it's shown really good average performance.
Right. But they need to do more research to see how it handles those really tough situations, you know?
Yeah.
The ones where you absolutely need a rock solid solution.
So it's like, we know the car can handle a smooth track.
Right, right.
But what happens when you throw in some ice and hairpin turns?
You want to know it can handle the unexpected. That's a great analogy.
What else did they mention?
Another thing was a lot of their testing, it was done on these synthetic networks.
Instead of using real world data.
Yeah, which is pretty common when you're in the early stages of research.
Sure.
But it'll be important to see how GDPG Twin performs when you've got, messy, unpredictable real-world data.
It's like practicing your golf swing on a simulator versus actually going out on a real course.
Exactly. Wind, uneven terrain,
Yeah.
all those real-world variables.
Exactly.
Oh, and one more thing they brought up, the design of the actor and critic networks.
The core of GDPG Twin.
Yeah. They said it might need to be tweaked for different types of problems.
So what worked in this study might not be the best for every RCOP out there.
It's exact.
So there's still room for improvement and customization.
Definitely. But that's what's so exciting about this kind of research. It opens up a ton of new possibilities and gets people asking new questions.
This has been a pretty incredible look at RCOPs and what machine learning can do to help us solve these really tough optimization problems.
It has.
Before we wrap up, what are some key takeaways our listeners should keep in mind?
Well, we saw how RCOPs are everywhere, right? They're in logistics, routing, data flow.
Right.
Being able to solve these problems well, it has huge implications for just about every field.
Absolutely.
This research, it gives us a peek into the future, a future where AI can guide us through these really complex challenges. It can help us make better decisions, be more efficient, and ultimately, it can make our lives better.
I know, I've learned a lot today. It's amazing to see how AI is evolving, how it's taking on these real-world problems that are constantly changing.
Yeah, it's really impressive.
So for our listeners, what stood out to you? Where do you see the biggest potential for this tech? We'd love to hear your thoughts. Leave us a comment below, and until next time, keep exploring and keep diving deep.